Hello, good morning, everyone. Can you hear me?
Yes, we can.
Yes, we can.
Yes, okay, wonderful. Good morning. Let's wait for a bit longer because there are only four of us, including myself at the moment. Hello once again. Do you have any idea why there are only six of us, whereas on Monday we had many more? Is it because Monday was just before the midterm? Do you have any
Probably.
idea why? No idea. Okay. How was the midterm? I'm going to mark it hopefully today, and you will get your midterm marks, which are 50% composed on the labs you have already done and 50% by the result of the midterm exam. Okay? So how was it?
Okay.
How was it?
Easy.
Easy, yes. I don't think it was any difficult. And the main emphasis of what we are doing in this course is not really the theory. The most important thing is your project work. And as you know, the course is largely project based. So our objective is really to apply various data mining techniques in order to generate meaningful and reasonable feature set for machine learning for the purpose of continuous price prediction. And using this set, you remember our first lecture that data mining partly overlaps with data analysis and machine learning as well. So having generated this set, we obviously don't stop at that point and we'll really try it out, because otherwise we have no idea whether this data set is any good or not, feature set. Uh, in the first part of our course and also today, there will be some concluding remarks about how this feature set is generated. And from next week on, you will have quite a lot of things to do actually in the labs which are going to receive today and tomorrow. So everything we have discussed on Monday, plus some techniques we are going to discuss today, they are to be implemented in the next cycle of labs, which is starting from today. Which means it's a little bit even too much to be done in 1 week, although not prohibitive. So we may allow a little bit more time to complete this, but we need to complete that as quickly as possible. Because from next week on, ideally you would still do it by Thursday next week, because this will allow you from Thursday next week to start already applying some machine learning techniques in order to process the feature set you are generating. And that would complete the end-to-end cycle of our data mining from, as you remember, data acquisition, normalization, descriptive statistics, to generation of feature sets and to machine learning trials. Okay, so this is going to be, I really hope, quite exciting. And if we do our feature set generation well enough, then our machine learning should really yield some useful predicting model for short-term behavior of instrument prices for those instruments which you are considering at the moment. And if it really works well, it may or may not be. We're only learning about how to do it. But if it works well, and if you are entrepreneurial and interested in this subject, then you may even try to run your own algorithmic trading strategy, although it will require a little bit more than that. You will need some connectivity tools in order to receive live rather than recorded uh, sheets for your orders for the market data. In the same way, actually, exactly in the same way as you receive it from the file, currently from the files. It would be exactly same types of, let's say, hello, apologies. The connection was lost for an unknown reason on my side. Maybe it was a short-term power cut. Can you hear me now?
Yes.
Yes.
Yes, apologies, apologies. So what I was talking about is that if this machine learning is done well enough, then in theory you would be able to run an algorithmic trading strategy based on that. Although it requires little bit more than just machine learning we will implement. You would need some real-time connectors and mechanisms for processing incoming market data, which would be coming in exactly same format as you are now reading them from a file. So it would be a sequence of orders with the action status like new, delete, or change, from which you would be able to build order books exactly in the same way as you do now. Only this will be done in real time. And also you would need a separate connector to place your own orders if you trade on the signals you generate, which is, I would say, still a kind of extensive infrastructure if we do it with all necessary detail. So a real life algo trading works in a way like this. No, definitely doesn't work this way. Let me change. Can you see? Can you see the whiteboard?
Yes.
Yes.
Okay. Um, it will be like this. Just a second. Okay, finally works. So in real life, you would have a connector which is called market data connector, which uses some internet protocol. If, for example, you connect to the Moscow exchange from a co-located facility, this is actually UDP for the fastest operation. So that's a link to the exchange. This market data connector feeds same orders as very similar sequence of orders as you get now from files. So basically the files recorded and which you are now using for your data analysis are precisely made using this type of market data connectors. So this is our order sequence, all order sequence, not only your own, all orders from the exchange. This is your or someone else algorithmic trading strategy. The strategy does exactly what you do. From those orders, it builds the image of the order book. Okay, first of all. And secondly, your strategy using this order book data, from this order book data, features are generated in real time. Obviously, all this is in real time. We do it offline, but the real trading strategy does it in real time. So features are generated, same features as you are now extracting from the data sets. Then there is a machine learning engine attached to your strategy, which consumes this set of features, perform the machine learning magic, and outputs to the strategy. Maybe I would depict it more clearly, not to here, but to another block of the strategy. It outputs the set of your orders. So basically, based on this machine learning information, you decide whether for example, to buy or to sell a corresponding financial instrument. So this is for all orders. This is for your orders. So the machine learning engine produces so-called signals for you, and this signal tells you whether to buy or to sell the corresponding instrument. Or maybe if you passively quote, you send limit orders to the exchange, you passively quote them, maybe not to buy or not to sell immediately, but just to change the price of your quotes. So for example, it could be your limit, let's say limit passive, as you know, limit aggressive, market, and so on. The orders are channeled back to the exchange through another connector, which is called order management connector. Market data connector is commonly referred to as an MDC, obviously market data connector. Order management connector is abbreviated to OMC. And then, actually, to make it more clear, the market data connector doesn't send anything to the exchange, it receives data from the exchange. So I would better put arrow this way. But the order management connector is both actually sending orders to the exchange and receiving the responses, because the exchange tells you, for example, whether the order has been filled or not. So the order management connector also maintains status of your current orders. So this is how an algorithmic trading platform in general looks like. So that's picture in the architecture. Simplified, of course. Of an algorithmic trading platform. The main components are, as you can see, the main components are a market data connector, your strategy, which in particular includes your machine learning engine, and the order management connector. In addition, typically there is an independent block independent of the strategy, which is called the risk manager. The purpose of a risk manager is to protect your finance, your budget from trading errors. It may very well be that due to whatever software faults, either, for example, in the strategy itself or in the order management connector, you start sending wrong orders to the exchange. And that way, you can very quickly, for example, do yourself a trouble and run into financial loss. For example, by placing a huge order on the wrong side of the order book. Although obviously the functional correctness is the responsibility of the strategy and all components in general, including the machine learning engine, the connectors, and so on, they must by themselves implement the corresponding checks in order to ensure the correct operation. But typically in real life algo trading platforms, there is also a separate overseeing engine which verifies, for example, your overall position, profit and loss. Position means how many contracts, for example, you have bought or sold. If you are supposed, for example, to do a market making, then you place passive orders on both sides of the order book, which are supposed to be, in general, filled symmetrically. So in general, your position, although not exactly zero, it must be close to zero when integrated over any extended period of time. So your market making strategy must not run into large positions. If it does, then the responsibility of checking this lies on, first of all, the strategy itself. But if the strategy, for whatever reason, is faulty, this is not the order book resides in the exchange. This is the order book image, obviously. If the strategy is faulty for whatever reason, or your connector is faulty for whatever reason, then unfortunately, this would mean that you do acquire an unreasonable position, and this can do you a lot of market risk exposure and potentially significant financial losses. So the risk manager typically intercepts all significant activities which occur, first of all, in your strategy, secondly, in your order management connector, and if something goes wrong, then it simply acts as a kill switch, stopping your order management connector from continuing operations, disallowing it, well, stopping it physically, just possibly killing it by a signal, uh, preventing it from sending further orders, and also the risk manager needs market data information, and therefore it receives this market data information from, again, one way, the opposite way, receive this information from the market data connector. And this risk manager is associated with some kind of database in which all significant info is stored, in particular all logs regarding to market data, your trades, and so on. So that offline analysis of your trading strategy performance, the decisions made by the strategy can be made. To this risk manager connector is typically, to the risk manager is typically connected the trading terminal, which allows a trader to monitor and possibly manually intervene with your trading strategy operations. So this is the trader's monitor. Although we're talking about a fully automated algorithmic trading operations in this case, through the market data connector, strategy, machine learning engine, order management, and so on. This is still obviously monitored somehow by human who, although is not capable of making a microsecond level, millisecond level decisions, is still reviewing the overall progress and the overall performance of a trading strategy. So, for example, the risk manager may stop the whole operations if your P&L falls under a certain threshold. So, for example, you encounter a certain loss, and the risk management engine, I would say not the risk manager, but the risk management engine. It's more to the point, because the risk manager could also be a person. Risk management engine would automatically stop the whole operations, and then the trader, by reviewing the situation, may conclude that there was nothing harmful about that. For example, the loss was small, and it is quite okay to press the button and restart the whole operation. Then the system restarts. So that's how what we are now doing. We are now in this, obviously, we have done order book image construction. We are now doing features construction, and our to-do in the machine learning engine. So that's what we are doing in this algo trading framework. But we are not doing at the moment market data connectors or the management connectors, risk management, DBs, monitoring, things like that. If you are interested in the whole loop in how to implement algo trading platforms, then one thing, well, you're now in your, sorry, third year, right? Or fourth?
Yes, third year.
Third, yes, okay. In that case, you have the whole, well, almost year and a half in front of you. And if you are interested in this stuff, then you may consider doing your, for example, final projects more focused on algorithmic trading. This is always possible. We do have such possibilities at our university. So if you are interested in the big picture, or maybe just a fragment of this picture, if you're interested more in how to do machine learning for algorithmic trading, then please let me know, and we may think about structuring such a project for you for the next year. This year, I presume you do have a course paper to be done, right? A coursework, a project in the third year, right?
Not everyone has to do a
What?
paper.
Not everyone?
You mean lean software development?
Yes, as far as I understand.
Oh, we don't have it.
Not everyone, okay, because I was thinking that all third year students are doing some kind of course project in the second term, in the spring term. If not, okay, but if you do have to do it and you are interested in this and you still don't have, let's say, subject for your project, then you may also consider something like this, then please let me know, okay? Fine. So that's how it fits in the big picture. Today, I would like to talk about two things. First of all, you remember the features which we discussed yesterday. So on Monday, the features which we are generating. The first feature is order book spectrum. All this you will be doing in your lab sessions also today and on Thursday, so tomorrow. You will be discussing this with Alex, and he will give you more detailed instruction of how to do this. So the first one is order book spectrum, but we were calling it 1A. You remember, but now normalized by maximum band, some kind of maximum band, as we call it. For example, 10M, 10M instead of 50 level cumulative quantity. The second is the inverse of the spectrum, which is precisely VWAPs for selected bands. BI. So, for example, we decided that it could be, for example, 100K, 200K, 500K, 1M, 5M, and maybe even 10M. So I would say 10M is the highest band. So in this case, I is there are six bands altogether. So 1, 2, 6. VWAPs for selected bands, and we also agreed that these VWAPs are taken relative to midpoint. You remember? And divided by price step, just for better normalization. Okay, that's what we did. Now,
can I ask a question?
Yes, please.
What does relative to midpoint means?
We discussed this on Monday. Let us recall what it means. So, for example, instead of just a pure VWAP, we compute the value like the following. So you take, for example, VWAP on, let's say, ask for a certain band BI. These are our BIs, all right? Minus midpoint. This VWAP is obviously greater than the midpoint, so minus midpoint is positive, and you divide it by price step.
Oh, yeah, understood. Yeah.
Okay. Or other way around, midpoint minus. It's a very good thing to reiterate, actually, because that's what you are going to implement. That's very useful. Thank you for your question. So midpoint other way around minus VWAP on bid BI, because now this VWAP is less than the midpoint, and again divided by the price step. Okay. Also on Monday, we agreed that the third feature will be bid-ask spread for the sake of normalization, also divided by the price step. Now, a much more interesting thing, we discussed it briefly, well, not so briefly, but nevertheless, let me repeat this. So number 4, the feature set number 4 is what we call liquidity taking rates. Liquidity taking rates. That's how this is ultimately important. This is how the liquidity is being taken by the aggressors. Who take the liquidity? Aggressors do, right? Taking means they fire up aggressive orders which match with passive orders in our order book and eat them up. So taking is eating up passive orders in the order book. In the order book. Okay, that's why there is a term taking. Taking means firing up aggressive orders. So basically what we need, we select now time intervals from t, let's say minus or plus k, let's say t minus k to t0, sorry, to t0, to t0 is the current time, and I propose that this t minus k are t0 minus 1 second, t0 minus 5 seconds, t0 minus 15 seconds, for example, t0 minus 1 minute for the moment. So k equals to 1 to 5. This is t minus 1, this is t minus 2, t minus 3, 30 seconds are missing, t0 minus 30 seconds, this is t minus 4, and this is t minus 5. Okay, then again, in the same way as we fix the bands, we fix those intervals. So for each interval, we compute for each interval t minus k t0, we compute the total quantity of aggressive orders. Let me taking or aggressive. So let's denote this by agar. Agar by for this interval. This is total quantity of aggressive orders within that interval, and that comes to an interesting thing, within that interval, where the aggressor is buyer. When you have an aggressive order in your orders log in the file which you process, then you know who is the aggressor. There is a flag, whether it is a buyer or seller, so you can tell who is the aggressor. And similarly, aggressive, I can say aggressive K, aggressive K cell, which is a similar thing, total quantity of aggressive orders within this interval, where the aggressor is seller. Okay. We have already discussed that at the end of the previous lecture, although I now put it in a little bit more detail. Can you tell me, please, so is it clear what kind of features we need to implement? So these are our features: aggressive K buy, aggressive K sell for K equals to 1 to 5, for example, and the quantities are computed this way. So is it clear?
So one feature is like a vector of 5 numbers.
Even 10, I would say. So
oh yeah, 10.
Feature 4, yes, consists of 10 numbers. 10 numbers altogether. That's true. This looks like more or less clear, but I would like to ask you, have you already been thinking about how actually this total quantity you are going to compute? Because this, you remember that this feature set is generated for each and every time instant when your order book is updated. So when the order book is updated, so you are now at T0. So T0 is every order book update time for a given instrument. So anytime when your order book is updated, you generate features 1, 2, 3 as discussed above. That's straightforward. Well, more or less straightforward, because those features 1, 2, 3, they only depend on the order book, right? So they do not depend on any aggressive orders, on anything. 1, 2, 3 only depend on the order book at time T0. So features 1, 3 are relatively easy. Depend only on order book, which you have already constructed at current time T0. But how are you going to compute feature number 4? At current time T0, you then need to look back and count the total quantity of orders which came into your order book, for the past, for example, 1 second or 5 seconds or one minute. And that is quite difficult because how we construct all the things, we move forward over our file, right? We move forward over our file. In real time, in the architecture which I have shown to you, not only you move forward over real time. So here, theoretically, at least you can really return to, let's say, several lines up your file, although it is quite difficult to do. Recalculate those quantities and fill in those features. In real time, you can't go back in real time when it is done in real time. So it is a problem. So does it require a look back? Obviously, we can't implement a look back. Instead of a look back, we need to do some kind of buffering of your information. So, for example, buffering of your aggressive orders. Look back, no, because cannot be done in real time. So we don't do it. Okay. Any ideas? Please, you are already software engineers at this point. So how would you propose to implement this feature?
We can have a data structure that we store like the aggressive orders that falls in our interval, and when we move in time, we have them sorted by time. And
Yes.
basically when the earliest one time expires, I remove it, and if a new one come, I push it in.
Exactly. You implement a buffer, a queue. So basically, this queue is, for example, this, let's say 5 seconds over time for a 5-second buffer. From one end of the queue, orders are coming into the queue, and from the other hand, they are removed. So an order comes into the queue, then it progresses over the queue, and when the 5-second interval, 5-second lifetime, 5-second lifetime of the order elapses, then it goes out of the queue, and fresh orders are inserted from the other end. All right. So an order is leaving in the queue only within 5 seconds. If we're talking about a 5-second buffer, in general, let's say it's any of those intervals, and expunged from the queue when this time elapses. So basically, this means that you need to implement 2 queues, all right? One, for example, for aggressive buyers, and another one for aggressive sellers. You place, actually, what do you place in this queue? You place quantity and time when it came, aggressive time for an order, and then every time when a new order, for example, is to be, actually any time when you use this queue for data processing. So when you compute the feature, you first of all review the queue, remove all outdated items from the queue, and compute your quantity aggressive by aggressive cell based on this queue. All right. So that's precisely, I think, what you meant.
Yes.
And obviously, this is the right solution. This is by far the best solution you can do. A very good idea. So, but if you, for whatever reason, consider that it is a little bit too complex to implement this type of queue, and we are now considering feature number 4. In addition to that, we'll be considering feature set number 5, similar, but related to liquidity replenishment or liquidity making rather than liquidity taking, as in this example. Then you know what, you will have to maintain quite a lot of those queues. Already here, how many queues are you are going to implement? You have 5 time intervals, and you have 2 sides, buyers and sellers. So yes, you need 10 numbers which are generated within this feature. So for each, you need to maintain a separate queue. So altogether, this means that you will have to maintain 10 queues.
We can make them one queue by adding one more state to the quantity, time, and type.
Possibly yes. So this is a good optimization. Well, one if it is an integrated queue, and then you just process it from the head to tail, да? Okay. Or one
I don't need to process it completely. I would like besides the queue, I will have variable, which is the sum. So basically, when the queue is empty, the sum is 0. Whenever I push something to the queue, I add it to the sum variable. Whenever I pop something from the queue, I subtract it from the sum. This way, I don't have to traverse the queue itself.
Very good, very good. Plus accumulators. A very good idea. So I think your solution proposed here is a very good one. And indeed, in real life algo trading engines, such high-speed queues are very commonly used. And if you implement your trading engine using some high-performance software technologies like C++, then there are highly optimized implementations precisely of queues and accumulators based on the property, based on the idea you have described. So you can have a look, for example, there is an open source C++ library, which is called UTXX. It is C++, unfortunately, not Python, and it has a buffer component, which precisely, or time buffer it is called, which precisely implement this type of behavior. But you know what? We can alternatively propose a less accurate, arguably less accurate, but nevertheless probably acceptable and much more simple solution. So this is definitely a very good solution. The first solution, look back, is no good. We know. This is okay. So this is minus, this is plus. There is another one. Interestingly enough, it is called on the data processing technique, which is used very often in digital signal processing, DSP method, digital signal processing method. You have probably heard about it, which is called EMA, exponential moving average. It is approximate. It would not give you exactly same results as your queues would do. The queues are perfectly accurate. But you see, we are going to use those data as features for our machine learning. So if we implement them in a slightly different way, but still capture the major properties of these features, then it is still okay, because the minor discrepancy may be automatically taken into account by the machine learning method itself. Yes, it will provide predictions based on a slightly different, but essentially logically very similar set of features, and we can expect that it will still be okay to base predictions on those slightly differently implemented features. So EMA, exponential moving average. Have you heard about it? Did you have any digital signal processing module yet in Innopolis?
No, it will be in the next block.
It will be. Okay. Great. Exponential moving average. The idea is very simple. So we need this, for example, this is n second. We need this n second aggregator, which we denoted by yes, agar k nk second nk second nk second quantity, which is our agar k by ocell. What we do? We define it in the following way, by a recursive relation. Initially, so this is your just variable. Let me denote it by, let's say, xk. Just to reduce writing. So that's your xk. What you do? Initially, you say xk to be 0. Then, anytime when you encounter just in your forward run, that's instead of buffering in forward run, an aggressive order, an aggressive, suppose that we're discussing the buy, aggressive buyers, an aggressive buy, because we're discussing buyers, an aggressive buy order of quantity equals to Q, then you do the following. You update your exponential moving average in the following way. You take into account the already collected average, and you take into account the new value of Q. This requires some care. So in the simplest case, but this simplest case might not work for us, we do it in the following way. So new value of xk is going to be some coefficient alpha. I would say simplest, but we'll need to modify it. It is some coefficient alpha times the new quantity which you have received, plus 1 minus alpha, which is the previous value of xk, previous value. So you update it this way. So basically, the alpha weight, because the sum of these coefficients is equal to 1. Alpha is in between 0 and 1. The weight alpha is given to the new quantity, and the weight 1 minus alpha is given to the previous tail. This way, exponential moving average is significantly different from the buffer we have implemented. So you see, one way or another, the exponential moving average keeps memory of all previous quantities entered into this xk. But the weight of the previous quantities is decaying and decaying and decaying, because obviously when you do yet another update, then you would have xk plus 1, xk, suppose that this is at some time t0. Then when you do it at the next time, same xk, at some time t, let's say 1 into the future, then it will again be the previous value, of course, is the previous, which corresponds to t minus 1. So you do it every time with every update. Then xk t1 would be alpha q plus 1 minus alpha x now k t0, which would be alpha q plus 1 minus alpha, and that value is alpha q plus 1 minus alpha xk t minus 1, and therefore you are getting alpha, and these are different q's obviously. So this is q at t0, this is new q at t1. So this is q at t1, this is q at t0, and therefore this is alpha q t1 plus alpha 1 minus alpha q at t0 plus 1 minus alpha squared, the previous value at t0 minus 1, and so on. So the tail, the previous history, is decaying as 1 minus alpha to the power n as you move away from any particular instant of time. So the tail, the previous values entered, are gradually going forgotten. This is the difference between EMA and your buffer, because in your buffer, the previous values get forgotten exactly after this n seconds. All right, so nk seconds passed, and the corresponding item is expunged from your buffer. In EMA, these values are never completely removed from the accumulator xk, but the older and older values appear to be appear with less and less significant coefficient, with small and smaller weight compared to the new incoming values, because 1 minus alpha power n obviously tends to 0. 1 minus alpha is less than 1. That's how AMA works. And this
I
might
have a
be...
comment on that.
Yes, please.
Like from what I understand from that, first we only can control like the time interval, although we don't have time interval here. We can control it only by alpha, and by increasing alpha, by decreasing alpha to make the time bigger, our average is delayed from the actual average. So like
You're absolutely right. And
so there is a delay in every transaction that we are doing.
that's true. So it does have some, first of all, yes, the value of alpha, you are absolutely correct about that. The value of alpha precisely corresponds to how much weight we associate with new incoming values, and how much weight we associate with the tail. So, for example, when alpha tends to 0, this means that new input unimportant, because it comes with a coefficient close to 0 in this case, unimportant. Almost all weight in historical values. This corresponds to, we didn't establish this correspondence yet very precisely. This corresponds to large buffer size. So this corresponds to large n seconds, where alpha tends to 1, new input outweighs the historical values. This obviously corresponds to small n seconds, but we still don't have any idea how alpha is related to this number of seconds, nk seconds, and we do need this probably.
We can estimate it by putting a threshold, for example, from a 10 to the -5. We will consider this value is deleted, and after, for example, if alpha is 90%, after, so we can calculate after how many terms to reach the threshold.
Yes, so we can, but in general we can do it. We can do it in a slightly different way. There is a notion of the period. There is a notion of the period in EMA. Obviously, there is no exact period because there is no curtailing, cutting off the buffer. So I can't say that the history is forgotten exactly after the period. But notionally, we establish such a threshold that after this period, we consider the tail to be small and insignificant. And by definition, the period is considered to be 2 divided by, sorry, alpha. Alpha is equal to, by definition, 2 divided by period plus 1. That's just a matter of definition, really. Where period is the number of updates. What is the period? Is the number of updates, not a temporal period, but number of updates. After which the history is considered to be insignificant. So what we can do is considered to be insignificant. What we can do in theory, we can say that obviously from this period, and what is the period? To compare it with our buffer, period is this n, how many updates? Period is this n k seconds times average, let's say average traits per second. So if you know this average traits per second, then you multiply it by nk, and you get period. From this period, you get your value of alpha. But we might not even need that. What you can do, you can simply forget about your seconds completely. What you do from this formula, you have that alpha equals to 2 divided by nk times average traits per second plus 1. The average traits per second is That's an interesting thing. The average trades per second in prime time when you run at let's say the most liquid operational period, let's say from 10 a.m. maybe until 15, something like that. This quantity is roughly equal to 1. It is different over different periods of time. So in general, if your NK is, as we say, 1, 5, and so on, then you can consider the corresponding set of alphas. So, for example, your alpha would be the smallest alpha uh, would correspond to the largest NK, which is obviously 60. The largest alpha would be 2 divided by 1 times 1 plus 1, 2 divided by 1 times 5 plus 1, and so on. So, by the way, the smallest, the largest alpha is going to be 2. By the way, the largest alpha in this case, the largest alpha is going to be 1 exactly. And this is unacceptable. This is unacceptable because in this case you give all weight, although it might even be okay. You give the all weight to the latest event or something like this. Probably this is not a very good idea to have it equal to 1, but let's consider the sequence. So in this case it is 2 over obviously 6, it is 1/3. The next one is 2 over 11, which is approximately 1/6, and so on. So what you can do instead, you can forget completely about your seconds, but instead you may associate just a certain sequence of alphas which you use in your update. So don't start with 1. 1 is a little bit too much. But for example, if you do your largest alpha to be 0.9, then let's say the next alpha going to be 0.3, and then maybe roughly each subsequent alpha is, so this is 1/6, so roughly do 1/2 of that, so do alpha, for example, 115. The next one is going to be oh sorry, did we use 10 seconds? No, we didn't. We used 15 seconds. My apologies. So this is 2 over 16, which is 1/8. Therefore, this is 15 seconds. Apologies. Therefore, it is 1 to 5, or you can approximately say the next alpha is, let's say, why not 1 to 5? You can keep it, and so on and so on. And then each next alpha would be, for example, about half of the previous, and only for the first alpha you have a gap of let's say 3 times. Then with this sequence of alphas, you can generate an alternative feature set which does not require buffering, but uses an EMA. It is not exactly what we meant, but it is close enough so that you consider that type of set. Is it more or less understandable?
Yes.
So you would use alternative. We don't know actually whether, let's say, a finite buffer or an EMA is the best idea. So you can use either of them, and these are two different ways of generating your feature set. Now, why this idea with alpha is probably good, because and you can later on you can play with the values of your alpha. Maybe you'll be better off with some different values, but for the moment I suggest doing something like this. Now we have the feature set number 5, feature subset number 5, because all of them 1 to 5, they form a feature set, and this is liquidity. As you remember, this is liquidity replenishment. This needs to be discussed in more detail. Again, what is liquidity replenishment? If you remember, we decided to do it in a quite tricky way. Liquidity replenishment are all orders of type. By the way, a very important point, the transformation, the analysis which we do here using this, for example, buffers or EMA is precisely, I would say, one of the core tasks of data mining. So implementing this feature generation using extended transformations like this, buffering, EMA, applying maybe some other filters, is precisely what data mining is concerned with. This is the essence of data mining. One of the very important things. So liquidity replenishment. By liquidity replenishment, we meant orders with passive orders, all passive orders with action equal to 0. Action equal to 0 means add. Do I remember correctly? Action 0 is add, all right? From the data set you are using. Is it correct?
Again?
You remember when you process your orders in the data set you have received, then there are actions for each order, and the actions are add, delete, or change. If I remember correctly, add is marked by 0.
I think it's add, delete, and max.
Add, delete, and change. Change means in place partial fill. All right?
Yeah.
So add is 0, delete is 1, part fill is 2, if I remember correctly. Is that correct?
Yes.
So
Yes.
add 0, delete is 1, 2 is change, but as we learned, you remember we discussed this, there is no in-place change, and the only change which can occur is a part fill. So the order was passive in the order book, it got filled, it got part filled, and as a result, its quantity is reduced in play. That's why it is changed. So liquidity replenishment is passive orders with action being 0, add, which get installed in the order book. That's precisely what you do in the order book construction, all right? At the corresponding level in bits or asks. Okay. Now the problem is, we definitely need these dynamics as well as feature, as well as liquidity taking to appear in our features. This is very, very, very important. But the problem is, as we discussed, those passive orders, they come at completely different prices. So for example, a passive order can get installed very deep in the rear of the order book, for example, very high in asks or very low in bids. And in that case, it is almost irrelevant. This order will not play any significant role in the near term price change in this order book, right? If it is inserted far away from the top of the book, then it is completely irrelevant. So what we do need is to consider the orders which come into the corresponding spectrum bands. So just a second, let me sorry for a second, go up and correct one thing. As we discussed last time, not only sorry, apologies, I have forgotten one thing and you didn't correct me. On Monday we discussed one more normalization feature here. So not only we compute those aggressive K by aggressive K cell, but we then normalize them. You remember? And I have forgotten to mention normalization here.
Normalize them by the viewer.
By time and by the maximum band. And then, so then the actual features, then normalize them. So after computing this aggressive K by aggressive K cell, either via buffer or via EMA, we normalize them, and eventually it will be aggressive K by and cell divided by max band, and we agreed that max band is 10 million, and also in the denominator would be n k seconds. So those are exactly features which we need to generate. Sorry for those lines. This is because I pressed wrong buttons on my pen. So we do need this. Okay. So that's the normalization which I have forgotten to mention. Now, exactly same thing we are going to do with the liquidity replenishment. So with liquidity replenishment, we also need to classify those orders where they are coming to. If they are coming into remote bands, they are much less relevant. So for this reason, we are considering those groups of price steps. You remember how we decided to do it. So we consider, for example, asks. I will do it in blue again. So we consider, for example, asks. And at any moment when a new order is installed in the order book, it can be installed into, let's say, first, second, and so on, fifth price interval, and this is the first group, 1 to 5. All right, then we have yet another one from 6 to 10, and so on. You remember those are which were used for construction of the spectrum. You grouped price intervals by 5. You remember this?
Yes.
So
But one question: how many passive orders comes per second?
once again, please.
How many passive orders comes per second in the order?
How many those inserted orders come per second? I would say if we, on average, we would say that not in terms of order number, but of order quantity, probably the overall rate of replenishment is about the same as the rate of order taking. So if order taking, we say about 1 trade per second, and 1 trade on average is 100K, for example, euros or dollars, then the overall rate of replenishment, I would say, which comes into 1 to 5, is slightly more than that. So it may be, for example, the total quantity coming 200K per second, 300K per second, something like this. So the total quantity being replenished, maybe 1 million per second, is several times larger than the taking rate, typically. So what you do, consider for the moment, let's for the moment concentrate on the first 5 intervals. Whether we need 6 to 10, I put a question mark here, possibly. But for the moment, just to get something done with feature generation, let's concentrate on the first 5 intervals. And again, and similar, let's consider the top of the book, 5 intervals from 1 to 5, but now the depth of the book corresponds to decreasing price, obviously, in bids, all right? So the first one is the top of the book. Here the top one, the first one is the top of the book. So what you do, in order to generate this feature set number 5, you do not consider all orders. Let's for the moment consider all passive orders which get installed into these low 5 asks, or I would say in price levels 1 to 5 in asks, and in price levels 1 to 5 in bids. So we will compute the quantities similar to liquidity taking. We'll consider liquidity replenishment. Liquidity replenishment within this period of time nk, or if you do not use a buffer, with the decay coefficient alpha, because you can do it again in the same way, either by maintaining a buffer or by maintaining an EMA with a certain coefficient alpha, which is the total quantity of passive orders. What is this liquidity replenishment? I give a definition. Total quantity of passive orders installed in price intervals 1 to 5 in it could be for bids and for asks, in bids or asks. So this is very, very similar to liquidity taking, which we have considered above. But now it is about liquidity replenishment. So again, it is the total quantity, and this total quantity is normalized by let's say by this max band, which is 10 million, and which is normalized by let's say nk. Obviously normalizing by nk is still better done if we use nk length buffer rather than alpha based EMA, but I think it is still okay to do it in either way. So, and these quantities again, there will be k times 2, 10 of them. They constitute the feature subset number 5. We may eventually need even to double this to consider maybe price level 6 to 10. I'm not completely sure. It might be. But for the moment, let's concentrate on those replenished in 1 to 5. Okay? In exactly same way, you compute this liquidity replenishment using a sliding buffer or EMA for passive orders, for the total quantity of, not number, but total quantity of passive orders being installed in price levels 1 to 5 in bids or asks within the time interval nk. Again, this will be from t minus k to t0, and this interval is nk seconds long. Or you don't use the interval, but you use alpha, alpha in EMA. In this case, you still maintain a notional length of the interval, but instead of using a buffer to compute this, you use this approximate alpha-based EMA. You will get more instructions on this when you start implementing this today and tomorrow in your labs. But I'm done for the moment.
Can I ask a question?
Yes, please.
It's about feature generations and particular about the third feature. Oh no, the first one. Order book spectrum. And for example, when we created it during the labs, we created 2 of them, like one for bids and one for asks. And when we told you about it, you expected us to create only one.
Order book spectrum obviously and critically needs to be done for both. For bids and tasks, these are different spectra and they are to be maintained separately, because it is precisely the imbalance between the two which may be a telltale of where the price is going to be. If, for example, you remember one spectrum, for example, on the bid side is very, I would say, dense, and there is a rarefied spectrum on the ask side, it probably means it is a sign that the price is going to move up. So order book spectra are separate for bids and tasks. The only difference here, which I proposed compared to what you have done previously, is that instead of normalizing the quantity in the spectra by total 50 level cumulative respective bid or ask quantity, you simply normalize it by a constant, which is 10 million here. So that's the only difference, but definitely separately for bids and tasks.
Okay, so we keep like 2 spectra for each.
Yes. Let me explicitly mark this. This is critically important. Separate for bids and tasks. You are right. Separate for bids and tasks. Yes.
But then don't we need an average spectrum?
The average spectrum was created for a different purpose. The average, in this case, no. The average spectrum was mostly created in order to verify that there are no long-term imbalances between bids and tasks. So in short term, such imbalances may exist. So for example, if you apply, we don't do it here, but if you apply the Kolmogorov-Smirnov criterion to bid and ask spectrum at a particular time, imagine that, right? At a particular time. Then the Kolmogorov-Smirnov criterion may very well tell you that they are different. And that's okay. That would precisely mean that the order book is unbalanced at the moment. And this is a telltale, one of the signals telling you that the price is going to move in a certain direction. All right. But what we have to verify with the average ones is that they are generally balanced on average. Because if they are not balanced on average, not only at a particular time t, but not balanced on average, then this average imbalance would somehow need to be taken as a feature as well. So this would mean that there is a systematic over the whole day pressure due to order book imbalance, which is probably going to move our prices just, as a momentum throughout the whole day. We learned that in general, this is probably not the case. So on average, they are balanced, but at any particular time, they may be imbalanced, and we precisely use them, including their imbalance, as features. But on average, they are more or less the same. So this is by itself an important information in our feature generation.
Okay, understood. Thank you.
Okay. Thank you very much, and see you next week. It may be. Tell me, please. So, next day on Tuesday, do we have a lecture on Tuesday, or it is Fatherland Defenders Day?
It's Tuesday and Wednesday at 9.
Is it not a holiday on Tuesday?
Oh, I don't know.
I don't know either. It
I
may
guess
very well
sometimes
be.
when we have holidays, we don't get it that day off.
Yeah, it is a holiday.
It is a holiday.
According to the latest email we received, yeah, it is.
Yeah. Oh, yes. So Tuesday 23rd is Fatherland Defenders Day in Russia. Great. So we'll have a lecture on Wednesday, and I can't tell you exactly. It may or may not be face-to-face offline. So I may or may not be in Innopolis at that day. I will try to. So I will let you know more close to that time whether it is going to be when it is going to be offline. Okay.
Yeah, okay.
Okay. Wonderful. Well done. Thank you very much.
Thank you. Goodbye.
Thanks. Bye.